Hello, this is the fourth video of a fourth Graphs and Network series on route inspection and the travelling salesperson problem for OCR Discrete Further Mathematics, and it looks at finding an upper bound. In the previous video, we introduced the travelling salesperson problem, where we want to find the shortest Hamiltonian cycle, i.e. that visits each node once only and ends up back at the vertex we started from. There was no algorithm for an optimum solution, and it was too time-consuming to check every possible cycle, so the strategy is to find a bracket of upper and lower bounds instead. In this video, we're looking to find an upper bound, which is the smallest one we can get, and therefore the nearest to the optimal solution. We want to find an upper bound solution to the travelling salesperson problem in a methodical way. We can use the nearest neighbour algorithm. Note that this algorithm will give a valid solution, but it is what we call a greedy algorithm, i.e. it takes the best choice immediately available rather than looking further ahead. Therefore it's a heuristic or doable rather than necessarily giving a particularly good solution. So the nearest neighbour algorithm is that you can choose any vertex as a starting point, and from the vertices that are not already selected, find the nearest vertex to the last one. It's important that you do not confuse this algorithm with prims, which allows you to find the nearest vertex to any already chosen. So in this algorithm, you only look at the nearest vertex to the last one you've just chosen. You then repeat step 2 until all the vertices have been selected, and finally you join that last vertex to the first vertex. In this example here, initially we'll start at A. And we can see there is a choice of 8 to B, 13 to C, or 9 to E. So we will choose the 8 to B, and I like to write them out with the numbers between the letters. Then, given that we only now consider the arcs coming out of B, we would compare the 7 between B and E, the 10 between B and D, and the 9 between B and C, and therefore that would be the smallest one, or nearest neighbour would be E at 7. From E, we're only considering the nearest neighbours to E. A has already been taken, as had B, therefore we could choose 15 to C or 8 to D, and the 8 to the D is the nearest. Now we're at D. We've already joined A, B and E, so we are forced then to choose the rather long arc of 14 to C. Having then joined all our vertices in the network, we just need to travel back to A, and we note that this is an arc of 13, again of which we have no choice. Adding up the 8, 7, 8, 14 and 13 gives us a total tour of 50. Let's consider what happens if we start at B. So, the nearest neighbour to B is E with 7. From E, we know that the nearest neighbour is D at 8. From D, given that we have already joined to E, the nearest one is A at 11. only now join to C, because that's the only vertex left, and we have to take that arc of length 13. C then now has to join back to B, and that arc is of length 9. So the total tour length for that, or the weight if you wish to call it, of that is 48. Here it is written out more neatly, but I would still recommend that you write the lengths of the edges between the letters to keep track of what you're doing. So in the example, we compared using the nearest neighbour algorithm with A as the starting point, and then with B, and you can see that we got different values, 50 compared to 48. So the rest of the nearest neighbour algorithm is to repeat for different starting vertices. And then when you've compared all 5, or n, depending on how many nodes you've got in the network, you then choose the least upper bound. Remembering we're trying to make the upper bound as small as possible. Here we have a table of results had we carried on beyond the A and the B, for which we got our 50 and our 48. So the other three results would be 48, 50 and 55. And you can see therefore that the B and C gave the least upper bound. So let's have a look and see. We can see that a segment of that, the EDAC, is the same in both of those tours. And indeed you've also then got C followed by B, both here and here. So it's not a surprise that the tours are of the same length. If we look at A and D as the starting vertexes, they are both of length 50 or weight 50. And although they don't look as if they've got that much in common, if you look at the segment DEBA, you can see that that is ABED in reverse. So in our network of 5 nodes, we will find at most 5 Hamiltonian cycles using the nearest neighbour algorithm. We've already seen that some of these could be the same cycle, either reversed or in effect shuffled along. It is important not to get confused between using the nearest neighbour algorithm at every node and checking every possible Hamiltonian cycle. Remember that in a complete network of 5 nodes, we would have had 5 to the minus 1 factorial over 2, or 12 different cycles, while the nearest neighbour algorithm only gave us 5 Hamiltonian cycles. So in that example, by looking for an upper bound, we can conclude that the solution to the travelling salesperson problem for this network is simply that the optimal solution will be less than or equal to that least upper bound of value 48. In the next video, we will look at a method to find a lower bound.